Hi, I'm Sosuke Ichihashi from Georgia Tech. I'm presenting Swarm Body, Embodied Swarm Robots, the work I worked with Kuroki, Nishimura, Kazumi Kasaura, Takefumi Hiraki, Kazutoshi Tanaka, and Shigeo Yoshida from Omron Sonic X and Cluster Metaverse Lab. Let me first introduce what the Swarm Body is. Here, you see many robots act as hands in concert, like the stars form constellations, or like atoms form our bodies. These robots as a swarm represent the physical hand. But why do we want swarm robots to act as our own hands? Let me explain that by reviewing the previous work. Which humans can view objects other than our actual bodies as part of our bodies? This fact was highlighted by the rubber hand illusion. The rubber hand illusion makes you perceive the rubber hand as your own. This illusion is caused by stroking the rubber hand and your actual hand synchronously. Later, researchers realized that you feel the virtual hand as yours if it moves synchronously with your own hand. Nowadays, this is widely used in virtual reality to intuitively control virtual bodies. Since it is easy to create various bodies in VR, researchers have explored what kind of body we can feel as our own bodies. In other words, they explored the limitation of our sense of embodiment. For example, they mapped the finger movements to arm movements, and it was still embodied. They also found that we can actually have a sense of embodiment towards multiple bodies. They even showed that we can feel a dog body as our own bodies. So this interesting work showcased how we can embody various bodies in the virtual space. However, these virtual bodies cannot act on the physical world, so they were more like fundamental perceptual studies. Some HCI and robotics researchers imported this knowledge to embody various physical bodies that can actually act on the physical world. For example, supernumerary robotic finger can help pianists play more notes. This intuitive control is the advantage of these embodied systems. Other researchers mapped the feet movements to supernumerary limbs to enable people to use 4 arms at the same time. So more and more works like these augment our physical bodies. However, there is a difference between physical and virtual bodies. That's the hardware. To modify our bodies in a certain way in the physical space, we have to develop a specialized hardware. As a result, we need as many different hardware as the desired augmented bodies. This also limits people with different body features to share the system. For example, supernumerary finger for adults cannot be used by children or babies. The same thing goes to the environment and interactions because the physical embodied systems are designed for specific situations. In addition, the user has to switch a device to switch between different bodies. How can various physical embodiment be flexibly achieved on a single interface like VR? How can we flexibly switch between these augmented bodies like VR? How can different users share the same embodiment system? A VR headset, or HMD, shows us various bodies through pixels. These pixels collectively form an image of our new bodies. Is there any similar phenomenon in the physical space? We realized that the physical alternative of these pixels is an animal swarm. This swarm acts as a shape-changing physical objects. Like a monitor shows us various virtual objects, they can form different physical objects or shapes. But if you look closely, this is just a collection of birds. Inspired by this, we designed physical swarm representation of our bodies. Swarm body may flexibly switch between different physical bodies, accept various user types and situations. We focus on a swarm of tabletop robots to explore the possibility of swarm body because it takes too much time and effort to train a swarm of birds to represent our bodies. Our primary question is if we can embody swarm robots as our own hands. So we investigated how various swarm robot parameters influence our sense of embodiment of the hand. First, we consider the density of robots. A dense swarm can show more details, while a sparse swarm is simpler. Next, even if the density of robots are the same, the position of the robots may influence how we perceive them. We developed and compared two position generation algorithms, bone-based and silhouette-based. Bone-based algorithm obtains positions based on the hand bone positions, so the positions are always fixed to specific parts of the hand. On the other hand, silhouette-based algorithm obtains positions by clustering the hand skin mesh, so the resulting positions are constantly changed and relatively well distributed over the hand. Another thing to consider is the robot assignment, because we have to determine which robots move to which obtained positions. We consider static and dynamic assignments. In the static assignment, the same robot always moves to the same destination. So even if the user turns the hand, the robot assigned to the thumb still moves to the thumb. In the dynamic robot assignment, the matching between robots and destination positions are constantly updated. So if the user turns the hand, the robot previously assigned to the thumb may change its destination to the pinky because it is closer. The last parameter we consider is the robot size. To sum up, the parameters we considered are robot density, position, assignments, and sizes. We run VR experiment to evaluate these parameters' effects on the sense of embodiment. We asked participants to conduct a reaching task. Various hand signs are shown on the table, and participants moved the swarm robots to fit them in the hand sign. We selected different hand signs to explore the levels of embodiment through various hand movements. After the reaching tasks, participants filled their questionnaire to evaluate the sense of embodiment. The results show that higher level of embodiment were experienced for both 20 and 30 millimeters robots. Moreover, there's a trend that the combination of bone-based position generation and dynamic robot assignment realize a higher level of embodiment than the others. And this is supported by the participants' comments that swarm robots felt like the hand if the robots were at the fingers, because bone-based algorithm always placed robot destinations at the fingers. 20mm robots tends to provide a higher level of agency, but it was higher than the neutral level for both 20 and 30mm robots. Next, we conducted the experiment in the real-world settings. Based on the previous result, we fixed the robot size to 30mm and designed the robot accordingly. This is the robot we designed. The robot wirelessly communicates with the dog and moves to the specific row positions. It has magnets at the bottom to improve its stability in the high-speed operations. Participants do the similar reaching task and fill the same questionnaire as a VR experiment. To track their hand movements, a hand tracker was placed under the table. The results indicate that bone dynamic led to a higher level of embodiment than the neutral. This is consistent with the VR experiment results. They also should suggest that the dense swarm and medium density swarm led to a higher level of embodiment than the sparse swarm. To sum up, our VR and real-world experiments revealed that swarm robots are likely to be embodied. We further explored the interaction possibilities of swarm body with a focus on physical telepresence. In this example, the user on the left is physically interacting with the ball on the remote table. Since swarm body can express various hand signs, the user can communicate through gestures. Swarm body also enables the user to physically interacting with the other people. In this example, the remote user provides haptic notification to the person. Leveraging the flexible and scalable nature of swarm robots, somebody can change its scale and form for different interactions and situations. It can also be divided into two swarms and can be merged back into one to support both one-handed and two-handed operations. This also allows another user to join the system. In this work, we showed that swarm robots are likely to be embodied through VR and real-world experiments. We also showcased various novel interaction opportunities taking advantage of this adaptable embodied system. We hope future studies deepen our understanding of the swarm embodiment and further explore its interaction space. Thank you for listening.